Hello everyone, my name is Karthik Gurjan. Today I will be presenting the solution to question 2 of the end semester exam paper. This presentation is submitted to Dr. Shaligram Prajapat sir. In this solution, we explore Bayes theorem and probability distribution using a student performance prediction scenario. Moving on to our first slide, scenario overview. To approach this question, we work with a dataset of nearly 5,000 engineering students. The dataset tracks the indicators such as attendance, test scores, and whether students submitted their video assignments. Our main goal is to predict which students are at high risk of failing their end semester exam. Early identification matters because it gives the college enough time to step in with support and corrective actions. Starting with Bayes theorem. We start the analysis using Bayes theorem, which help us update the probability of an event whenever a new evidence becomes available. In this context, it updates the probability that a student will fail based on signs like poor attendance. The formula written as PH by E gives us a posterior probability, the updated belief by combining the prior probability with the likelihood of the evidence. Defining hypothesis and evidence. Using historical trends, we define the hypothesis and the evidence. Hypothesis. The student will fail. Historically, around 25% student fail. So, P of fail is equal to 0.25. Evidence. The student's attendance is below 60%. The likelihood value. Among the students who failed, 85% had low attendance. Among the students who passed, only 15% had low attendance. Now, the basic calculation. First, we compute the total probability of the evidence P of E, which comes out to 0.325. Then, using Bayes theorem, we divided the probability of low attendance among failing students by the total probability of low attendance. The final results come to approximately 0.6538 or 65%. This means that if a student has attendance below 60%, the probability of failure jumps from original 25% to around 65%. Next slide. High-risk classification and intervention. Based on the updated probability, the student is placed in the high-risk category. This approach removes guesswork. It enables target actions like academic mentoring, remedial classes, and continuous monitoring. Colleges can use such predictive models to reduce failure rates effectively. Moving on to the next question. Binomial distribution. The question also involves probability distribution. First, the binomial distribution, which models the number of success in a fixed number of trials. For example, if we pick 20 students at random and the historical pass rate of 0.7, we can estimate how many out of those 20 are likely to pass. It even let us calculate precise outcome like exactly 15 students passing. Next, Poisson distribution. The Poisson distribution used for modeling rare or random events within a fixed time interval. Take an example, during exam week, a teacher receives an average of 5 doubt clearing emails per hour. Poisson distribution helps predict how many emails might arrive in the next hour. This becomes useful for scheduling teaching assistants and managing workload. Next, the normal distribution. Finally, we look at the normal distribution, which applies to continuous data that clusters around a mean. Marks often below this pattern. Marks often follow this pattern. If the average marks is 55 with a standard deviation of 10, scores arrange themselves into a bell-shaped curve. Using the imperial rule, we know that 68% of students will score between 45 and 65. At last, we get to conclusion. To conclude, we have applied Bayes theorem to identify individual failure risk, binomial distribution to model pass-fail outcomes, pass-fail counts, Poisson distribution for predicting resource demand, and normal distribution for analyzing overall student performance. Thank you, Dr. Shaligram Prajapat sir, and thank you everyone for listening.